Hi, so I'm Doug Watt. I joined Imagination about a year ago, and my role was basically to look at OpenCL and work with some of our leading customers. And at that time, there was probably one or two customers who were actually looking quite seriously to take OpenCL into production. And when I say into production, I mean actually using OpenCL for their own purposes to do something within the mobile space. Then more recently, I've been spending quite a bit of time talking to some of our customers and working with the sales and marketing guys to really try and understand what the requirements are for OpenCL and sort of some of the emerging use cases for mobile compute. And actually one of the things which is probably most interesting and which this presentation will cover is that in the mobile space, some of these application use cases which we're going to talk through, they are actually probably just about possible with a CPU, but the power consumption, the power budget, it's just not possible to get these things into production. And so where the GPU is really adding value is in getting the power down. So power is today's problem. In the past, first it was transistors, so you just didn't used to have enough transistors to get all the functionality that you wanted, but Moore's law has been our friend. And then after that, there was issues with bandwidth, but thankfully, again, we've been able to design higher bandwidth memory interfaces through improving DRAM technology. And then today's issue is really thermal shutdown. So it used to be the case that for every process step, you could reduce the threshold voltage of the transistors, and then that would allow you to lower the power supply. But today, things like leakage, they get worse and worse per process step. That's why ST have gone to silicon on insulator. And so I've got a few slides really just to try and to highlight this without being too scientific or... But for example, here's a YouTube video which shows 3 different mobile phones running a CPU benchmark. I believe it's Drystone. And as you can see over time, the mobile devices heat up to the point that you can actually melt butter. And some are better than others, but actually, this is everyone's problem. That's the CPU side. On the GPU side, here's an example of a graphics-heavy games benchmark, which a number of different GPU vendors and looks at some of the performance. So on the x-axis here, we have time, and typically with these benchmarks, they run for about 30 seconds. This one's actually quite long, so it's running for a couple of minutes. And then on the y-axis, we have power and watts. Well, lower is better. So the blue and the red lines, these are 2 different GPUs. Both of them are tile-based renderers. So in terms of graphics rendering, if you have a 3D scene, one of the things you can do is you can effectively use a tile-based render to reduce the amount of overdraw, and that generally improves the power. So a straight line is very good. The red line is pretty good, but the sort of zigzag there represents a little bit of clock management that's going on. Then the green line, this is an immediate renderer, so there's less, so there's a bit more overdraw here, so the actual total power is going to be a bit higher, but actually, it's still pretty good. And then we have one more device, and this is actually a tile-based renderer. But what you see here is a number of spikes, and then a couple of really big spikes. And what this is actually representing is the device effectively going into panic mode and shutting everything down for a period of time until the thermal sensors record that the die temperature has dropped. And what this means effectively is you get about 25% in performance hit. So this is not particularly scientific, and it's just one example, but it's intended to illustrate the point that actually this is a problem today. And so I guess looking at things like this, the question then is, well, what do we do about it? So this is a sort of bit of a marketing slide, but again, to illustrate the point, let's say you have a pretty stressful benchmark running on a phone. One thing you could do is you could cool it down, and as a result, you're going to get a lot of performance. And this is actually a genuine case. We actually heard that one recommendation to FutureMark was to cool the device down, and as a result, they were able to get twice the performance. So what are the kind of solutions, and these have been talked about this morning already, but one of the things we can do is we can go parallel. So things like VLIW architectures and SIMD, they let you do more per clock cycle and therefore run the device slower, therefore it's more power efficient. Multiple threads and multiple cores, pretty standard techniques, but you can't just keep adding more cores. And actually this was something that recently I think Qualcomm was very verbal in saying that you can't just bring 4 hammers to the construction site, you need to bring the saw, the screwdriver, and so on. And actually, if you look at things like Windows phones today, they probably use just 1 core. Maybe they'll go and turn on another core in the next generation, but no one's really using 4 cores today. And they're certainly not going to use any more in the future. So that kind of brute force methodology doesn't scale. So then you can potentially look at going heterogeneous, and modern SoCs, they're already very heterogeneous, so they mix all these different components from CPUs, GPUs, DSPs, and so on, custom logic. And the nice thing there is that each of the blocks is optimized for a different kind of computation, therefore runs that computation the most efficiently and at the lowest power. And different SoCs are put out into the market aimed at different classes of applications. And ideally from the software programmer's perspective, you're going to target every application task to the hardware block, which can execute it the most efficiently. And today we have fairly coarse-grained granularity between the CPU and the GPU, but with things like HSA, that will allow us to do more in the future. So one of the interesting things with GPUs is they now employ the same kind of parallel features as CPUs. So things like SIMD and threads, you have this kind of SIMD execution model and lots of cores. And whereas in the past they were special purpose, historically they were just fixed functions, but more recently they've been special purpose shader engines for graphics. Now they're really evolving into more general purpose programmable devices. And what effectively we're working towards is this, you can sort of think of it as a computational block where you have efficient latency processing through the CPU and efficient graphics and some form of data crunching, so efficient throughput processing on the GPU. And what we have today looks a little bit like this. So the CPU has a number of cores with a small amount of parallelism and a big cache which gives you good latency throughput. And the GPU has a number of sort of high vector SIMD processing elements with smaller caches, and in the mobile space they tend to be connected with a unified system memory, although there's a dispatch overhead to move work from the CPU to the GPU. So the question is, what are we going to do with this kind of architecture? And what we're finding from speaking to customers is that the use cases they have for mobile compute, they have to be practical, and by practical, what that means is they tend to be things which don't require computation at the same time as you need to be rendering 3D graphics. So for example, computational photography is probably where we see the most interest from customers. So things like HDR, where you're going to take a lot of pictures, maybe different shutter speeds, and then combine them all together to get a really nice picture, or the kind of panoramic stitching kind of algorithms that you see with the phones, where you kind of do a 360 and it stitches it all together to give you a panoramic shot. Fisheye lenses, where cheap lenses, you need to do some correction to make the image look good. And all these kind of use cases are all, typically you want good response time from the phone. So you're going to take a picture, and within a second or so you need to be able to take the next picture. That's kind of interesting for compute because the images are getting bigger, the resolution is getting higher. So if you can offload the GPU, you can save a bit of power. But potentially what's really interesting is when you move this stuff to video. So if you look at some of the recent extensions that have been pushed through Chronos for this, you can potentially now take data from the camera straight into the GPU as an OpenCL image and then start doing some processing on it. So things like real-time camera previewing effects. So for example, you could be using your phone, perhaps taking a picture of someone and then in real time doing things like changing the color of their eyes or their lips or whatever kind of image processing you want to do. HEVC decoding is something that's been mentioned before. That's an interesting use case because it's a time to market play, but eventually those things will be hardened down into ASIC logic. Then maybe the encoding is interesting on the GPU. The reason the encoding is potentially interesting on the GPU and maybe a good use case for HSA is that actually it's probably going to take a couple of years for the algorithms to really mature, and OEMs may want to compete on who gets the best picture quality for a given bit rate. And then we've got one thing at the bottom called risk mitigation, and it's a little bit irritating from our perspective, but there's a number of customers who don't really have any use cases for OpenCL, but they're concerned that with things like RenderScript, that potentially, let's say this stuff all gets pushed into TVs in the future and then someone goes and makes an app that uses it, that they don't want to be seen to be poor on performance. And actually, lots of people are benchmarking things like the Google SDK examples and so on. So it's kind of, you have to be able to show some performance on these benchmarks. But it's not particularly helpful in actually evolving the architectures. So that's what practical compute is. What is probably not, and what we tend to see quite a lot of in marketing materials, things like games physics. For the most part, the games developers, when you speak to them, they say we can't give them enough graphics as it is. So the last thing they're going to do is start using this device to push a load of physics through the GPU, for the most part. There are one or two cases, things potentially like lighting, where you're already using GLSL to do some of the computations. So maybe you do a substitution, do an OpenCL. But for the most part, it's not games physics, and it's certainly not high-performance scientific computing. The kind of stuff that people write on desktops, they don't port them to GPUs. The use cases for mobile GPUs are completely different. But for many of the practical use cases, programmability is a requirement. And we had examples there for vision, for example. That's another area where there's a lot of work going on in terms of vision algorithms, things like automotive, safety systems, and again, if you were to harden all that into ASIC logic, you would prevent yourself from evolving those algorithms over time. So where programmability is a requirement, either because the algorithms are changing over time or there's a standard which is not yet ratified, that's a big win for computing on a mobile GPU. And our point would be that the architectures which are optimized for those practical use cases are going to be the ones which provide the best performance power trade-offs. So one of the things that you can do when designing a mobile GPU is look at the ALU design, which our architecture team actually did this, and they looked at the different rounding modes that are mandated by different compute APIs. So if you think back in the graphics-only days, faithful rounding was what was typically used, and that's not compliant to any particular IEEE standard, but it's good enough. Then things like the OpenCL embedded profile mandate round to 0. What we found was that consumed on average about 15% more power than faithful rounding. Then round to nearest even, which is what's required by the full profile, typically used in scientific applications, also by RenderScript compute, that requires another 15% more power. And probably the key point here is that if you have a GPU and you've put in, let's say 64-bit round to nearest even, full profile, you pay that cost for all of your use cases, even if 80% of your use cases are graphics. And when we're starting to think about heterogeneous computing and different compute units for different tasks, you really need to question whether that's what you want in your GPU. For RenderScript compute, we don't actually have any customers that are taking that stuff through to production at the moment, but we can sort of get away with it by whitelisting. And we do have this stuff on the roadmap, but it's something that I think deserves some attention and conversation. So what Imagination have done for their GPUs is they've taken all the things from the full profile as well as the embedded profile that don't require this sort of high power cost. And that's what we provide OEMs and through OpenCL drivers that are starting to emerge on phones. That's something that developers can use as well. What we've been very cautious about is putting things like 64-bit and high precision rounding in because of the power cost and because we see the use cases as primarily high performance computing. Certainly for some of the image processing, which is a key driver to a lot of these use cases, you will not notice a difference between a color value of 203 and 204. It's very difficult to tell. And we have an example of this, and this is kind of an old demo. But what we show here is we have some image processing running on a Panda board with a fairly old GPU now. And we have 3 modes. We have single thread, dual thread, and GPU. What we show at trade shows and so on is that when you move from a single to a dual and then to the GPU, you get a power performance trade-off, and this is effectively what it looks like in terms of the energy processed per frame. So there is a real win to be had with a GPU that's designed for power to then offload some of these computations to that GPU. So Simon's already talked a bit about HSA this morning, so probably all I really need to say is that we're on this evolutionary path towards process designs that combine both the efficient latency processing and the efficient throughput processing, and much tighter integration of all these different components. And it's not just ALU design. We need, as a company, to analyze the emerging use cases to determine the right balance of hardware for each new design, from things like the ALUs, how many do you need, do you provide, optimize the floating point or integer, what's the precision requirements, what do you do about local memory, do you provide as registers or SRAM, or perhaps just let the caching hierarchy take care of it. And then even the ISA. At the moment, the ISAs tend to be optimized for graphics, but as we have more emerging use cases in different application areas, there may be particular types of instructions that you would want in your ISA to enable more efficient static compilation. In terms of coherency, what we have today isn't full HSA. We do have some level of coherency between the CPU and the GPU. In terms of, it's one way the GPU can set some flags on memory accesses that allows sometimes not having to go to system memory, which is potentially a power save. On the other hand, that doesn't fit some of our use cases particularly well today, particularly where you're taking data straight from the camera into the GPU. So there are a few interesting use cases around what we have today for coherency. But really, it's the kind of evolution that we're on to HSA. One of the key benefits of HSA, whilst you may add more area and more power to deal with HSA infrastructure, at a system level, if you can reduce power, then you've won. And this zero copy, so the ability to process data from different processing elements without having to move it around, and that's one of the issues today is you often have to make copies of data to move between different spaces. When you don't have to do that, potentially you're onto a win. We'll skip through this slide since we've already seen it in the previous presentation. And again, just to kind of look at how things have changed. So a few years ago, if you look at the chart on the left, we probably had 3D graphics as the entire use case. So we were very optimized for that. Then, over the last year or so, we're starting to see these emerging use cases appear. And on top of that, with HSA, we've then got all the use cases from CPU as well. So we now have this mix of computational requirements that we may need to address within a single processing unit. And as an IP vendor, there's a value chain, and we provide IP to a silicon vendor who makes a chip, provides it to an OEM. They release a phone, for example, and then app writers come along, write some code. And we're kind of lucky today because a lot of these companies that are doing OpenCL are vertically integrated, so they do perhaps 3 of those components. But it's, from our point of view, it's really interesting to understand the kind of applications that people are writing so we can use that to drive future hardware development. And that's what we're starting to look at today quite seriously. So really, just to summarize, I think what I'd like to emphasize is that we're moving towards this world in which we have increasingly heterogeneous integrated systems in the future, and there's this potential for fine-grained distribution of tasks pretty easily across different compute units. And in this sense, we need to think about how we architect these things. If we have very high precision FP64 requirements, perhaps we should allocate them to the CPU. Perhaps we shouldn't be overloading the GPU for this or over-specifying it. In fact, recently I heard there was a mailing on the Kronos mailing list suggesting that the embedded profile will be dropped from OpenCL 2.0, and is this a good idea? I think people are starting to equate OpenCL 2.0 with HSA. But maybe there's value in having the kind of features in HSA, such as a zero copy with low power ALUs for mobile space. And at a conference like this, where everyone is focused on low energy, this is the kind of stuff that I think we should really be talking about. Thank you.